So in the last video, we looked at polynomial or a single term of a polynomial, x to the nth power, and taking a derivative of that. That's a very important tool. After that, trig functions are very, very important. We saw some applications in a different playlist of how anything with sine, cosine show up in oscillations, as well as different force vectors. So a lot of times they will show up as important things to consider. And derivative is just a rate or gradient show up a lot of places too. So we're going to look at the fundamentals of derivatives of trig functions, specifically sine and cosine. Everything else can be really derived from those two, but we'll also look at tangent in this video, and we'll derive it straight from the limit definition of a derivative, and then in the future we'll derive the other three using quicker methods. So we're going to take first we're going to start with sine of x, right? So our function is sine of x, and we're trying to solve for the derivative of sine of x with respect to x. That's why it's written as d sine x dx. And then we'll do it for cosine and tangent as well. In order to do it with the limit method, we do need to use some trig identities and recognize the limit's effect on sine and cosine. So what we're going to say is that we're going to take the limit of a function where delta x, right, so a small step size, is approaching 0. And it's going to be important for us to understand how this is affecting sine and cosine separately. So for cosine, so delta x approaching 0 is basically along this x-axis. So if it's very, very small value, right, basically 0, so if that's true, then we could say cosine delta x is equal to 1. Now for sine, we know that sine of 0 is equal to 0. But if it's very, very small, it's approaching the delta x, in fact, right? So we don't want it to completely go away because that's not true. It's not truly equal to 0. And 0 versus something very small are very different values. So when we say limit delta x approaching 0 for the function sine delta x, we say that that is equal to delta x. You might see this in terms of theta on other problems, right? Limit theta approaching 0 for sine of theta is equal to theta, right? So that's going to be important, and that's going to show up in some of these derivations. And then we have these forms as well, right? So let's take a look at our limit equation, right? So this is just a pure definition of the derivative. As we said before, dy dx, or f prime, however you want to write it, it just means we're taking a derivative of the function f or the function y, right? In this case, we're going to look at sine of x first. And the definition of the derivative says I can take a limit of the step size, delta x, as that gets smaller and smaller, right? So it's very small step size. And then I could just do rise over run definition. So y, or the function, at some x plus delta x, minus y, or the function, at some x location. So we take two y values at different x locations, one at x plus delta x, one at x, right? And we divide that by the step size delta x. So all we do is we take our function, plug in x plus delta x for this term, and we take the same function and plug in x for this term, and we try to simplify it, right? And then at the end, we'll take the limit and see what falls out from it. So our function is sine of x. So I have sine x plus delta x, that's my yx plus delta x term. Then I have minus sine x, that's my yx term, divided by delta x. So I want to expand this sine x plus delta x. So I can use my trig identity. I have sine theta plus or minus phi right here. Theta is going to be my x term. We're going to have plus, and then phi is going to be my delta x term. So I can basically rewrite this term and swap out my thetas for x and my phi's for delta x. And that's what's showing up here, right? So I have a sine x times cosine delta x. That's showing up here, plus cosine x times sine delta x. That's this section in here, right? So this is my yx plus delta x term, minus sine x. All right, now I can do the substitutions that we talked about earlier, right? So here, my cosine delta x, I can replace this with 1. Sine delta x, I can replace this with delta x. Okay? So then my equation simplifies to sine x times 1, that's sine x, plus cosine x times delta x, that's the term right there, minus sine x. So that's my numerator. So remember, we're still taking this at the limit of delta x approaching 0. Sine x and sine x cancel out right here because of subtracting. And I'm left with cosine x delta x over delta x cancel out. And I'm left with cosine x. So the derivative, this is the derivative of sine x dx. Okay, so memorize that. The derivative of the sine is positive cosine. We'll do the same exact process for cosine. So now we're going to apply the same logic to our cosine term. We'll use some of these trig functions again. So again, there's my definition of the derivative. And now I plug in cosine x plus delta x for my yx plus delta x term, and cosine x for my yx term. And I want to expand this one. I have a different trig function, or trig identity, to substitute. So we have plus or minus, and over here it's minus plus. So I have a plus sign here, so that will match. So when I use this right side of this equation, I'm going to use a minus form. That's what. So there is a distinction between plus or minus up here versus minus plus. Okay, so we'll do that substitution now. So cosine x, cosine delta x, that's this term right there, minus sine x, sine delta x. That's this term right there, right? So we're just swapping the thetas for x and the phis for delta x. All right, now we can use the relationship between cosine delta x, as we see right here. This will just be 1. And sine delta x, this will be my delta x term. Okay, so cosine x times 1 is cosine x. Sine x times delta x is sine x times delta x, right? That's that term, minus cosine x. So cosine x, so these terms will cancel. And I'm left with minus sine x delta x divided by delta x. And then these terms will cancel. And I'm left with negative sine x. So the negative is important, right? So when you take the derivative of cosine, you get a negative sign. When you take the derivative of sine, you get a positive cosine. So this is your derivative of cosine x with respect to x. Okay, so these two honestly show up over and over. So it's really important that you remember these. With future videos, when we talk about like product rule and quotient rule, you'll see that these alone can give you the identity for the remaining 4. But just for completeness, we'll solve for the derivative for the tangent term using the same exact method. All right, we're going to repeat the same process for the tangent function. So we have tan x plus delta x. That's my yx plus delta x term. I have tan x, that's my yx term for my numerator. And then that's my rise, right? And my run is delta x. And we're going to take the limit as delta x approaches 0. So again, I have a tan x plus delta x, so I need to use a trig function to simplify this. And I have this term right here. Remember, my thetas are going to be swapped with x's. My phis are going to be swapped with delta x terms. I have a positive sign here, so I'm going to use positive, and down here I'm going to use negative. So I'm going to swap this out, and I get this term right here. So this term right here is this equation, which came from this guy right here. Okay, And then to get to my second step, I need a definition for tan delta x. So you see a tan delta x show up right here. And you see one showing up right here, right? So I have sine delta x limits and cosine delta x with a limit of delta x approaching 0. And we see that right there. So we take advantage of that. Since I know that tangent is sine over cosine, I could say limit delta x approaching 0 of tan delta x is equal to the limit of delta x approaching 0 of sine delta x over the limit delta x approaching 0 of cosine delta x. And I know for sine delta x, that's delta x, and for cosine delta x, that's just 1. So this is just equal to delta x. So I can put a delta x right there, and that's this guy right here. And I can put a delta x down there, and that's this delta x right there. Okay, so next, what I want to do is take the subdenominator right here, which is 1 minus tan x delta x, and I want to incorporate it with this tan x term, just so I have a better way to start canceling terms out. So I'm going to multiply negative tan x by the quantity 1 minus tan x delta x. And let's see what we get. All right, let's focus on this term and slowly move across here. So, all right, so multiplying by this denominator here shows up right here, right? The 1 minus tan x times delta x, right? So the numerator up here, tan x plus delta x, that's remaining right there. Then I have the negative tan x, so negative tan x times the quantity 1 minus tan x delta x. Okay, so that's all contained there. Now I can multiply my tan x to this quantity. So I get a tan x and then a tan squared x delta x term. All right, so I'm just expanding or just multiplying that tan x through the system. Okay, so now I have a tan x here and I have a negative tan x here. So those cancel out. Let me use a different pen color. So this tan x and this negative tan x cancel out. And I'm left with a delta x minus a negative tan squared x delta x in my numerator. But my denominator still has a delta x times 1 minus tan x delta x. Okay, so how can we clean this up a little bit? I can pull out delta x, right? So this delta x and this delta x give me delta x times quantity 1 plus tan squared x, right? So 1 from this term plus, because minus times minus, tan squared x. That's where this numerator comes from. I haven't done anything to the denominator yet. Okay, at this point, at this step, my delta x's cancel out, and I'm left with just one last delta x. I can set it to 0 from the limit component. So then I have 1 minus tan x times 0, which is just going to be 1. So it's basically this is equal to divide this numerator divided by 1 minus 0. So that's like I can just drop it out. Tan squared x can be rewritten as sine over cosine squared x, or sine squared x over cosine squared x. And I'm trying to force the use of this trig function, sine squared plus cosine equals 1. As I said, when we're looking at the tangent video for the identities, this is the most common form that I see show up over and over in derivations. So sine squared plus cosine squared equals 1 shows up a lot. So we can force that to show up here, right? So if I make cosine squared a common denominator, I'm going to have cosine squared plus sine squared over cosine squared, which I'm forcing that identity right there. So there I have it right there, sine squared plus cosine squared over cosine squared by just making this a common denominator. And then I can use the identity that this numerator, let's use black, this numerator is equal to 1. So then we have 1 over cosine squared. And remember, cosine is equal to secant. So we get secant squared is equal to derivative of tangent x with respect to x. Right? When we get to the video that we talk about quotient rule, we'll see that we could do this much simpler just by knowing the two fundamental cosine and sine derivatives. All right, so let's take a look at some graphs. One thing a lot of my students forget is whether the derivative of sine is positive or negative cosine, or cosine is positive or negative sine. They remember they're swapped, and one's positive, one's negative, and I can show you you can use a graph or the unit circle to help you remember the sign, whether it's plus or minus. So let's take a look at our graphs. All right, so now we can take a look at these graphs. So the most common thing from students is they'll say, I know the derivative of sine is either plus or minus cosine, and the derivative of cosine is either plus or minus sine, and they forget whether it's a positive or a negative for each case. So the way I tell my students to think about it is, you can sketch a sine graph and you can sketch a cosine graph. Even if you don't remember fully, use your unit circle, and it's pretty intuitive, at least for that first phase. So in solid red right here, we have the sine x graph. And if you forget, remember, you just draw your unit circle. You say at 0 degrees, you're at the positive axis, x-axis, so your y term is equal to 0. So sine x is 0. As you go up to 90 degrees, or pi over 2, you're rising to a 1, right? The unit radius, 1. So you're rising. So that means you have a positive derivative. At the peak right there, you have a slope of 0. So then you would graph cosine. Cosine, you know that you have a positive 1 at 0 x-axis, and then you rotate until you hit 90 degrees, and then you're at 0, x equals 0, so cosine would be 0. So you're going from 1 down to 0, but you're in the positive regime, right? So if you're deciding between plus or minus cosine x, you know it's going to be positive just by graphing this from 0 to pi over 2, 0 to 90 degrees. Because you know if it was negative cosine, this dashed line would be mirrored across this x-axis. All right, so then let's say, all right, now I know it's derivative of sine x is positive cosine x. Then you're asked to take the derivative of cosine, and you know it's either plus or minus sine. You can do the same thing to test, right? So the solid blue line here is my cosine. That's the function I'm trying to take a derivative of. Then you watch the first section here. You know, you start at 1 because it's a positive x along the positive x-axis, and you drop down to 0. So you're going to have a negative slope right here. And then if I just peer over to my sine curve, which is the solid red one, we know that first section is a positive value. So I know that I need to throw a negative sign in front of it, right, to mirror it. And that's showing up in this dash curve here. So combination of using your unit circle and sketching a first part of the oscillation for sine and cosine can quickly help remind you whether the derivative is going to be a positive or negative value. All right, so we can take a look at tangent and think about along the same lines. Let's say, and here we're not defining the function itself, but just defining whether the shape of it or the signage of it makes sense, right? So tangent, we have these oscillating graphs as well. It's positive. The slope of this curve right here, if you follow my cursor, is positive, positive, positive. It reaches a inflection point of sorts, and then it gets positive, positive, positive. So this secant squared graph in the dash reflects that, right? It's all positive, not the slope, but the actual value of this dash is all positive, reaches something like an inflection point here, and it remains positive, right? You're at max values at these vertical asymptotes. And your other trig functions have similar behavior. I'm not going to derive them for you here. We'll derive them when we look at the quotient rule. So you have your cosecant, which is negative cosecant times cotan. The derivative of it is. And so it's solid. You have your cosecant, and your dash, you have your derivative. And it's positive. It almost mimics similar behavior in reverse of this tangent, right? So the solid, you have a negative derivative across your zero slope, and then a positive till nearly infinity, and then mirroring across, right, in this oscillation. And that's what we see here. Similarly, for secant, we have seen a similar behavior with a phase shift, not surprisingly. And then for cotangent, this one looks very similar to the derivative tangent. So we can reflect on this again when we look at the quotient rule. But the main thing to remember is you want to memorize this derivative and this derivative, and then use your unit circle to recognize just that first phase in both of these graphs to help make sure you have the signage correct. Just from this alone, you can build upon it with some of the other rules that we're going to teach you in future videos, and have the ability to solve for many complex trig derivatives.